Hello, I'm Mazafar Zadeh, and I'm here with another episode in the Solar Energy Training Series. The topics we'll be covering in this lesson are as follows. We'll review solar systems, explain the photovoltaic effect, and discuss what we'll examine how PV modules are made together. The different types of solar panels will be discussed, and we'll compare the various types of solar panels. The Apowar brand solar panels will be introduced and presented, and finally we'll have a conclusion. In previous sessions, we talked about the different types of solar systems. We said that solar systems fall into three main categories. The first category is off-grid, the second is on-grid, and the third is hybrid systems. One of the key components of solar systems is the solar panel, which is common to all types of solar systems. Without it, a solar system is practically meaningless without a solar panel and doesn't really exist. Now that we've understood the necessity of having a solar panel in a solar system, let's get to know this important component of solar systems better. The photovoltaic effect is one of the key phenomena in a solar system, especially in the process of converting sunlight into electricity by the panel. The word photovoltaic is made up of two words, photo meaning light and voltaic meaning electricity. To better understand how this effect works, we divide it into three stages. The first stage is the collision of energy particles. Sunlight consists of tiny particles called photons. When these photons hit the surface of a solar panel, which is usually made of silicon or the same, when they enter the silicon structure, they gradually transfer all of their energy to the surrounding atoms. The release of electrons is considered the second stage of the photovoltaic effect. When solar energy reaches the atoms, it causes the electrons to become excited and released. The third stage of the photovoltaic effect is the generation of electric current. Solar panels are designed in such a way. Silicon generates current. The orderly movement of these electrons is what we call electric current or electricity. A simple example to better understand this is an air hockey table. Try to imagine that photons are like the physical impacts you deliver directly to the pucks. NP junctions guide electrons like pucks on a table, creating current. No fossil fuels are used here, making solar energy a clean primary source. On the table, flow follows the balls after being struck, moving toward the exit. This process uses no fossil fuels, making solar a clean way to generate electricity. Curious how a solar panel is made? Let's look at the process. And to get more familiar with the making of panels and the process involved, I invite you to pay attention to the educational video that will be played next. A solar panel is made from a material that you might find hard to believe, sand. Yes, ordinary sand, which is mostly made up of quartz, is the main basis for making solar panels. Quartz is composed of silicon and oxygen. Silicon, or what we call silicon, is the second most abundant element on Earth after oxygen. Turning sand into electricity is an adventurous journey for this material, and you will accompany it in the following segments. Silicon is Earth's second most abundant element after oxygen. We'll follow its journey from sand to solar panels, starting with the extraction and purification of silicon from rocks. Extracted rocks, mostly quartz, enter massive furnaces at over 2000 degrees. Next, we melt silicon into ingots. At these heats, silicon separates from the molten rock, the basis of glass, computers, and Pakistan. The highly purified molten silicon is carefully collected, and then it enters a series of specialized molds where it is solidified and turned into the large, heavy ingots you see here. At this specific stage of the manufacturing process, you can have two distinctly different types of ingots. This is a solar panel. Purified silicon is molded into the large ingot seen here. This process produces two types, cylindrical monocrystalline ingots and cubic ones. At this stage, the ingots are cut and turned into wafers. The ingot is sliced with a very thin steel wire and turned into extremely thin sheets, about the thickness of a strand of hair. Next, the ingot is sliced into hair-thin wafers using a fine steel wire. These wafers serve as the base for solar cells. Both sides are then smoothed to remove any burrs or irregularities. This further enhances the overall thickness of the wafer, as well as its central core. After this stage, an electric field is created inside by printing aluminum metal lines onto the wafer, forming a grid to collect the current. After that, by diffusing phosphorus and boron, a PN junction is formed, which is one of the refining the wafer, aluminum grids, and phosphorus-boron diffusion form the vital PN junction. Next, wire the cells in series and parallel to form a panel. Then stack the previously mentioned layers. These layers are detailed below. Before the panel is delivered to the project executor and the buyer, various tests are performed to ensure its accuracy, such as EL tests and crack detection tests using cameras. Next, a junction box is attached before final delivery, following EL, infrared crack, and environmental stress testing. UV and impact tests are done with precision to ensure high efficiency and quality. Final checks, including battery and inverter connections, prepare the panel for solar use. It's a difficult journey, but the effort to produce clean energy is worth it. As you saw in the video, each panel is made up of a specific number of solar cells. Each individual cell has its own specific current and voltage, and in fact, it functions as a PN junction. The voltage of each cell is usually only about half a volt, which is quite low for most applications. To achieve a much higher voltage and current in a single panel, these solar cells are connected together in series, just like what you saw in the video. You can see this clearly in the image provided here. In this view, you can see the different layers that make up a panel. You might also wonder how these fragile cells are protected so that the panel can be used in any weather conditions without being damaged. The answer lies in the structure of the panel's layers. This layered structure protects fragile solar cells from weather, ensuring durability and performance. Next, we will provide a concise yet thorough explanation of every individual layer and the specific function it performs. The first layer is known as the frame layer. Its structure is usually made of aluminum, and its role is to provide the panel with mechanical strength. Next, we'll cover each layer's function. First, the aluminum frame provides mechanical strength, protection, and mounting support. Second is the backsheet. It is made of high transparency tempered glass, and its function is to maximize the transmission of sunlight and protect the cells against impact, rain, dust, and hail. The next layer is the encapsulant layer with high adhesion. Its structure is a transparent polymer layer, which is usually made of EVA. The primary purpose of this component is to hold the solar cells in their proper place and provide a robust shield against moisture and external vibration. In the next layer are the solar cells themselves. It keeps the solar cells in place, protecting them from moisture and vibration. The next layer contains interconnected silicon cells, which convert solar energy into DC electricity. This layer is the heart of the solar panel. And the next layer is again a protective layer, or the upper EVA layer. Its structure is similar to the third layer, made of upper EVA, and its function is to provide additional protection for the cells from the back and to increase the lifespan of the panels. The next layer is the backsheet, or the back layer, or the backsheet layer. Its structure is a multi-layered polymer sheet and acts as an insulator. Its function is electrical insulation, preventing moisture penetration and protecting the panel from the back. Finally, the junction box layer, or the connection box, is usually a box located at the back of the panel that this polymer sheet insulates and protects the back. The junction box houses terminals and diodes to collect and connect power. And it also prevents reverse current. I will explain more about bypass diodes in the next videos. And it also prevents reverse current. We will explain more about bypass diodes in the next videos. This was an introduction to the different layers of a solar panel, which I hope has been useful for you. Keep in mind that the solar cell is the smallest unit used to convert light into electricity. By carefully placing individual solar cells next to each other in a series connection, a complete solar module is formed. And by placing these modules together, by placing solar cells next to each other in series, a solar module is formed, and by placing modules together and connecting them, arrays are created for large and small solar energy projects. Up to this point, you should have become generally familiar with how panels are made and their internal structure. Now, the important question that arises here is whether all panels are the same and if there are no differences between them. Panels work together to deliver clean energy, but are they all the same? How are they classified and on what basis? We will explain this in more detail next. The first category is monocrystalline. The second category is polycrystalline. Solar panels are generally divided into three categories. The first category is monocrystalline, the second is polycrystalline, and the third is thin film. These differ from each other in terms of structure, color, efficiency, lifespan, and some other factors, which we will explain and examine further. Monocrystalline panels are made from pure silicon crystals. They have a dark, almost black color, offering higher efficiency and performance than the other two types while occupying less space. Due to this, these panels are typically used in areas where high efficiency is required, such as cloudy regions where maximizing output is essential. Better for cloudy climates, polycrystalline panels are easier to make than monocrystalline ones as they are made from multiple silicon crystals. Their non-uniformity hinders electron flow, resulting in lower energy output. And they have lower efficiency compared to monocrystalline panels. Their appearance is characterized by a blue color close to navy. These panels have a very suitable temperature coefficient, which is why they are recommended for environments with very high temperatures. Thin film panels, also known as film panels, are considered the second generation and more modern than the first generation crystalline cells. These cells are made by placing one or more thin layers of photovoltaic materials, such as amorphous silicon, onto glass, metal, or plastic. Their main features are low weight, flexibility, and low efficiency. They are used in situations where we need panels to be flexible. These panels are a suitable option. Comparing panel types, monocrystalline versions usually have cut or rounded corners in newer generations. Sometimes they aren't cut sharply. Their dark color is a main visual feature, making them easy to recognize. Their dark, near black color makes them easy to spot. Polycrystalline panels feature square cells with sharp edges. Their navy blue color and visible crystal grains make them easy to identify. Thin film panels are placed on glass surfaces as flexible, semi-flexible, or completely flexible sheets, forming a smooth, even layer. You can easily identify them by their lightweight, thinness, and sometimes their flexibility. So here we have learned how to distinguish a panel by its appearance and determine what type it is. Next, we want to examine the panels in terms of their internal structure as well. The internal structure of monocrystalline panels is as follows. Let's take a look at the cells of a panel. Looking at the internal structure, monocrystalline cells are built in a uniform and orderly way. As shown here, their atoms align regularly in the same direction, which creates a much simpler path for electron movement. And for this reason, they have higher efficiency and performance. The internal structure of polycrystalline panels is such that they are made up of several crystals placed next to each other. While others offer higher performance, polycrystalline panels consist of multiple crystals. Their varying orientations create boundaries that hinder electron flow, resulting in average efficiency. Compared to monocrystalline panels, they have lower efficiency, and compared to thin film panels, they have better efficiency. But as mentioned, they have a more suitable temperature coefficient. As you can see in the image, thin film panels have a disordered structure, and the atoms are arranged irregularly next to each other. They have lower efficiency compared to the other two types. But it has the ability to be flexible. It is recommended for applications that require this flexibility. Here, we want to give a general summary of the important parameters of the panels. As mentioned, the efficiency parameter for monopanels, but it has the ability to be flexible, and it is recommended for applications that require this flexibility. Here, we want to give a general summary of the important parameters of the panels. As mentioned, the efficiency parameter. Monocrystalline panels have the highest efficiency due to their internal structure, and then polycrystalline panels have medium efficiency. In terms of appearance, monocrystalline panels are the ones that are monocrystalline in nature, They are cut, and thin film panels have a uniform surface, and usually their cells are not very distinct. The cost per watt is usually higher for monocrystalline panels. Polycrystalline panels are moderately priced, and thin film panels have the lowest cost and the lowest price. The space required per monocrystalline panels require less space for a given wattage. Polycrystalline panels need a moderate amount of space, and thin film panels, because they have lower efficiency, if we want to reach a specific wattage, we have to use more of them, so the required space increases. The performance of monocrystalline panels have good efficiency, polycrystalline panels offer average efficiency, and thin film perform very well. Contrary to belief, rising temperatures will actually decrease panel efficiency and overall performance. Since all panels have a temperature coefficient, exposure to extreme heat leads to significant performance losses. Here, a parameter is defined for panels called the temperature coefficient, which determines up to what temperature the panels can maintain their efficiency. For example, polycrystalline panels, because of their blue surface, have better efficiency in places with very high temperatures compared to monocrystalline panels, since they have a higher temperature coefficient. Flexibility. As mentioned, monocrystalline and polycrystalline panels do not have flexibility, but thin film panels and some of their models can be flexible. Finally, regarding the application of panels, monocrystalline panels can perform very well on residential rooftops and in limited spaces, as well as in places where the climate is cloudy. Polycrystalline panels can also be used in the same situations, and they are even suitable for use in medium-sized power plants. Thin film panels are used in specific surfaces and industrial projects. To give a simple summary, monocrystalline panels have higher efficiency. Cloudy side polycrystalline panels balance cost. Industrial thin film is less efficient, and monocrystalline is high efficiency but expensive. But they are stable, logical, and suitable for specific conditions. To determine which panel you should choose, you can consider the following factors. The conditions of the installation site. Consider the amount of sunlight. These flexible panels suit special conditions. Use this checklist to decide. Consider your site's sunlight hours, average temperatures, and factors like dust or humidity levels. How high is the probability that there will be shading caused by nearby tall buildings, leafy trees, or even atmospheric pollution in your area? Furthermore, the availability of physical space can often become a significant issue. Do you have space limitations? Is your roof small? Do you need high efficiency? What type of installation do you need? Can it be installed on the roof? Consider shading, space, or roof size. Do you need high efficiency? Will it be roof, ground, or mobile mounted? What about the angle and direction? How is it? The next thing you need to consider is the climate conditions and performance. Does it perform well in low light? Does it perform well at high temperatures in your environment or not? Is resistance to dust and pollution a very important parameter for you? Check the technical specifications of the panel. What is the panel's efficiency, its nominal power, temperature coefficient, voltage, and its operating current, as well as the panel's annual power degradation rate. Make sure to check these before purchasing. Another very important point is compatibility with other equipment. Your panel should be compatible with the inverter and with the battery in off-grid and hybrid systems, of course. Matching the voltage and current with your system. These are calculation matters that should be addressed before buying the panel. You definitely need to take that into consideration. Warranty and the manufacturer's credibility are also among the important factors in choosing a panel. You definitely need to take that into consideration. Warranty and the manufacturer's credibility are also among the important factors in choosing the right panel. What is the warranty policy for the product? Is this warranty reliable? Does the brand have a good track record in panel production or not? And also the cost and economic efficiency of the panel, the price per watt, installation and maintenance costs, return on investment, total life cycle cost. These are all factors to consider. These are all the essential factors you need to take into account and carefully evaluate before selecting and purchasing a panel. One of the most important factors in choosing the right panel is understanding the differences between the various brands available, as each manufacturer offers unique features and different levels of reliability. And it is a reliable brand. APO is a manufacturer that offers panels with a variety of wattages. This brand produces and supplies panels in both polycrystalline and monocrystalline types, ranging from 10 watts to 720 watts to the global market. This brand is one of the most reputable brands. It is a brand whose panels, after passing technical stages and obtaining the necessary standards, have been able to be used with excellent efficiency in both small and large power plant projects. In this video, we became familiar with the structure of panels, their types, and how to choose the best panels, and we reviewed the important factors for selecting a panel together. In the next videos, we will become more familiar with important panel parameters, their configuration, and various other topics related to solar systems. We appreciate your time and thank you for your attention.